Today's topic is 2D vector operations. If you have ever walked, rode a bike, rode in a car, or drove to school in the morning, your morning starts out with vectors. Bearing problems are an example of this. Vector problems like this are called displacement. A typical problem could be a runner runs in an easterly direction for 4 kilometers and then turns in a southerly direction for 2 kilometers. To get a handle on this kind of problem, we should probably talk about bearing first and what that means. If you're familiar with a compass or a map, you'll notice that down here I have a symbol of direction that you would find on a map. And it's oriented just like a compass. This direction up points to north, and this direction to the right points east, and then down is south, and then to the left would be west. Normally when we're talking about an angle, we're starting at the x-axis and traveling counterclockwise. Then when we're talking about bearing, we're starting at north and moving clockwise. Different. So if I am traveling east, due east, well, the angle that I'm traveling at is on a bearing of 90 degrees. Just like this. If I'm traveling in south, then my angle is 180 degrees because I'm halfway around the circle from north. And west would be 270 degrees, all clockwise from north. So in my situation here, my runner runs in a easterly direction. Oh, there goes the whole thing. Hold on. Okay, that was a little sloppy. My runner runs east for 4 kilometers and then turns and goes south for 2 kilometers. And you'll see my vectors here. This vector here, oops, give me a second. This vector here has a length of 4 units, and then my other vector here going south has a length or a magnitude of 2 kilometers. This vector here, well, it's not a vector yet, but now it is. That measures the direction that I'm traveling from my starting point here, and it's also how far I've gone. That's called displacement. Oh, look, guys, that's me running. Not only am I going really slow, but I'm going in the wrong direction. Okay, back to my bearing problem. If I wanted to find out my displacement, or how far I'd actually traveled from where I started and the direction I was going in, you can see here that, oh, we thought we were done with trig. No, sorry. You can see here that I actually have a right triangle. Right there. And I have my angle here, I have the adjacent, and I have the opposite side, and I can also find this hypotenuse here if I use the Pythagorean theorem. So why don't we do that first? Let's find out the actual displacement, the actual distance I am from my starting point. So to do that, I'm going to use a squared plus b squared equals c squared, and my sides are 2 squared plus 4 squared equals x squared. That'll be 4 plus 16 equals x squared. So 20 is equal to x squared, which means x equals plus or minus square root of 20. In our case, a magnitude is always positive, so we're going to take the positive solution. and x is about 4.47. So I'm actually 4.47 kilometers from where I started. Now if we want to find the angle, we can go ahead and use the tangent ratio. Actually, we could use any of them, but the tangent's going to be the most accurate because these are original exact values. So tangent of theta is 2/4. I need to take the arctangent or the inverse tangent of both sides, and that gets rid of it, unattaches it from the angle. 2/4 is 1/2. And I end up with an angle here of 26 degrees-ish. Actually 26.6. But if I'm talking about bearing, and this is east, I haven't taken into account north yet, right? And this angle is actually 90 degrees. So when I'm calculating or figuring out the direction I'm going, I'm on a bearing of 90 plus 26.6, which is about 116.6 degrees, right? Because from north, I've gone all this, I'm going around another 26 degrees from east. Hey, but why would we let the fun stop there? Let's get the family together and take a trip. To my favorite place on earth, Yellowstone National Park. Hold on a second while I get my family. Here they are. Oh, look how excited they're jumping up and down. They can't wait to go to Yellowstone. Kids, step away from the geyser. You'll get burned. They're getting bigger now, so that I hope they all fit in my car. Okay, kids, you ready to go? Get in the car. Yay! Great, I got everybody in. Hopefully we don't get pulled over on the way because the police frown on putting kids in the trunk. Okay, so we're on our way. And do you know that every time we change direction even slightly or change speed, we're adding another vector. And so by the time I get to Yellowstone, I've traveled in my car a distance of 2,359 miles. But if I look at the straight line distance from where I started from, that's here. Pretend that's straight. That's 1,937 miles, and or roughly that. So that's the displacement, and that's what we call a resultant vector. It's the actual displacement that we end up. It's what happens when we add all these thousands or even maybe millions of vectors together. Where I started from and where I ended, straight line distance, that's called my resultant vector. All right, let's get mathy with vectors. So we can add vectors, and there are 3 steps to that. So step 1, if we want to add vector A and B, we first draw vector A. I'll make that thick. Okay, vector A, and it has to have a direction and a magnitude that represent that vector. Okay, step 2. Oh, that was step 1. This is step 2. I'm going to pretend that this is vector A. Okay, step 2. at the arrowhead end, of my vector A, we're going to draw vector B. So we start here, draw vector B. We do this tip to tail. Right? The tip of vector A is at the tail of vector B. Okay. So now step 3, join at the beginning of A to the arrowhead at B. That'd be vector B. Just like this. Beginning of A to the arrowhead of vector B. That is vector A plus B. Okay, so here's an example with A and B with two actual vectors. Let's make these vectors black and we'll make the resultant red. So following my steps, we start with vector A, and you can see that it goes over 3 units and up 1, 2, 3, 4. So I need to go over 3 units and then up 4 for my end. And I'll draw as straight a line as I can under the circumstances. So this is vector A. All right, and then I'm going to put the tail end of vector B to the tip end of vector A. All right, so vector B starts here, it goes down 2 units and then over 1, 2, 3, 4. So I'm going to need this to start here and then go down 2 and then over 4. 1, 2, 3, 4. So vector B is going to need to end there, and that's vector B. Okay, so A plus B, let's change colors, starts here at the beginning and ends at the end of vector B, or at the arrowhead. So that is vector A plus vector B. And A plus B is my resultant vector. Kind of like result, haha. There we go. Here's one for you to try. I have 2 vectors, vector P and vector Q. I want you to stop this and try it out for yourself. When you're done, restart it and check your answer. Okay, you can see we have vector P over here. It goes to the right 1 and up 3. So if I start that here, I can start it anywhere. I could draw that vector anywhere I wanted to, as long as it had the same direction and the same length or magnitude, it would be equal. But I'm going to start mine in the corner, make sure I have plenty of room. So over 1, up 3 means it's going to end there. So that's P. Vector Q goes over 2 and up 2. So over 2, up 2. Oh, it's a good thing I started there. I would not have enough room if I didn't. My resultant, oh, forgot to write P or Q. My resultant vector starts at the beginning, ends there. So that's my resultant vector P plus Q. Hopefully you got that right. Here's another one for you to try. Try that, stop this, and then try this out. When you're ready, start it back up, and we'll go over the answer again. Okay, so I want P plus Q. I'm going to start with vector P. Vector P goes over 5 units, so 2, 4, there's 5. So there's vector P. And Q, you'll see it's attached to the tail, but I want the tail to be at the tip of this one. So tip to tail, this goes over 2 units and up 3. So I need to go over 2, up 3, means I'm going to end there, draw my little arrowhead, and then when I draw my resultant vector, I start here at the beginning and end at the tip of vector Q. Oh, I forgot to write Q. Imagine that. Me forgetting something. Okay, so there's my resultant vector P plus Q. Okay, so here we're going to use this diagram to show some interesting properties of vector addition. Here I have P to S equals P to R plus R to S. You'll notice that I don't have P to R. There's no line here. Where's that laser? There's no line here from P to R. So I have to make that. I just have to. Let's make that red. So if I want to get P to R, that's actually vector A plus vector B. That will give me P to R. So that's A plus B. Oh look, P to R is A plus B. And then I'm going to add C. So from P to R, or A plus B, I'm adding C. I'm starting at the tip of A plus B with the tail of C, and that's here. That's R to S. Okay? And let's draw our resultant in, oh, let's use yellow. I don't use yellow very often. From the beginning to the tip of my last vector, that's P to S. Or A plus B plus C. A really interesting question is, does the order matter? Does A plus B plus C here equal A plus B plus C? Well, to answer that question, I need to pull out my little eraser. Yay, I found the eraser. Okay. So we've already shown that A plus B plus C, that equals vector P to S. So if I start over here, let's go with vector A. So we'll draw vector A with red. We're starting at P, there's vector A. I need to take a detour for a minute and figure out what B plus C is. So if I start at B and go to the end, and then I pick up C at the tip, I'm going to draw vector B plus C from the beginning of B, ending at the tip of C. So this is B plus C. That's this. All right, I'm going to add these two vectors together. Vector, is that my laser? Vector A plus vector B plus C. And when I do that, oh, let's use yellow then. Starting at my starting point and ending there, I get vector A plus B plus C. And look, I end up with vector P to S. They are equal. That shows that vector addition is associative. I bet you haven't heard that since middle school. Okay, here's a property for you to try out. Why don't you see if vector addition is commutative? On this side, in this graph, well, I have vector P over here and vector Q is over here. Hey, that's a round vector. No, just kidding. All right, on this graph, I want you to do P plus Q, and on this graph, I want you to do Q plus P, and you can stop this and then restart it when you're done, and we'll try it out yourself. We'll go over it when you come back. Okay, so for vector p, right here, I'm going to start with p, and then I'm going to add q to it. I need to go over 4 units and up 3. So 1, 2, 3, 4, up 3. That puts me about there. And then vector q is right 1, down 2. So that's going to end here. All right, and then my resultant vector is here. This is p plus q. This is p, this is q. All right, pretty unremarkable. Now let's try q plus p. So because q is pointing downwards, I'm going to need to start at the top somewhere. So let's start here. Let's go to the right 1 and down 2. There, that's a reasonable drawing of vector q. Starting point. Oh, you know what? This guy goes up. So he'd have to go this way. I'm going to erase and move vector q down a little bit. And oh, not with the laser, I'm not. Okay, there we go. So let's see, start with q. We need to move q down. Need a pen. Okay, let's move q down to here. Give that a try. Is that going to work? No, you know what? That's still not far enough. Not the laser. I need to move q all the way down to fit it in the grids. All right, so starting here, ending here, that's q. And then p moves over 4, up 3. So from here, I'm going to move over 4 and up 3. So I'm going to end there. And now I'm going to draw my resultant vector. This is q plus p. Now, it might look different because it's in a different spot. Where's that laser when I need it? Okay. But if you look at it, it's pointing in the same direction. And it moves 1, 2, 3, 4, 5 to the right, up 1. This one moves 1, 2, 3, 4, 5 to the right, up 1. That means that these two vectors are parallel, they're moving in the same direction, and they're the same length. So they are equal. So these are both equal to each other, and that's a true statement. So vector addition is also commutative. In the last video, we talked about negative vectors. I'm just going to remind you that my vector a here, it's the same length as negative a, and it's parallel to negative a. The only difference between a and negative a is this arrowhead. Okay, they are going in opposite directions. They're the same length, but they're going in opposite directions. In fact, if I were to add a and a together, a plus negative a, I would get 0. And that's the 0 vector. So we're going to talk about vector subtraction now. If you want to subtract one vector from another, let's say we want to subtract b from a. So a minus b. Well, we're going to do the same thing we do for vector addition. We're going to add them, but we're going to make b a negative vector. And how could I make b here a negative vector? Well, it's easy. I'm just going to change the direction of B, and I'm going to put the arrowhead down here. And then I proceed in exactly the same way. So I start with A. I have to move over 1, 2, 3, 4, 5, and up 4. So 1, 2, 3, 4, 5, and up 1, 2, 3, 4. Okay, so arrowhead goes at the end. I have A. Now B, I'm going to make this the starting point and this the tip. And that moves over 1, 2, 3, and then down 2. So for B, I'm going over 1, 2, 3, down 2. There's my endpoint. And my resultant vector is A plus negative B. This is negative B here. And that's how you subtract two vectors. Okay, I have a few more examples to show you. I'm going to do r minus s right here. So that's going to be r plus negative s. R is a easterly due east vector. 1, 2, 3, 4. I have to go over 4 units. And then s, it points up like this, but we're going to reverse the direction and turn it around. Okay, and it moves down 3 and to the left 1. Oops. Pardon the herd of elephants that just ran by the room. I forgot my little tip here. Okay, so this would be r plus negative s, where this is r and this is negative s. But that looks a little sloppy. I could use a bigger grid. Okay, so this time I'm going to go all out and subtract 2 vectors from s. So it's going to be s minus or plus negative t plus negative r. And let's see what kind of mess we end up with. Just erase this guy. Okay. So I'm starting out with s. He moves up 3 over 1. And then negative t. Oh, yeah. Oh, no, that works. I have to switch him this way and start here. And so that's over 2, up 2. So right 2, up 2 is going to put me here. So this is negative t. This is s. And then negative r. Oh, I'm going to go off my grid. I think I can handle this, though, because it's a straight line. So negative r starts here, ends here. 1, 2, 3, 4. Okay, and then my resultant vector, I'm going to go ahead and add that in, is this. So this right here is s plus negative t plus negative r. Okay. Here's one for you to try. I want you to find r to s with using the diagram, then s to r, then vector st. Stop the recording, try this out. When you're done, you can restart it. And we'll go over the answers. All right, let's check this out. So for vector rs, that means I have to start here and end here. And for that to be in terms of the other smaller vectors, that means that my starting point for my other vectors, because I'm starting here with r to s, that has to be where I start my other vector. So you can see that it's vector r, but I have to switch the direction because it points in the direction it's moving. So that's going to be negative r, and then I start s and head in its normal direction, so plus s. That is negative r plus s. By the way, I could also write that as s minus r, and to prove that to you, I'm going to draw that situation in blue. So if I do s here, and then I subtract r, or add negative r, that's a vector with this magnitude and direction. So I'm going to do my best to replicate that. That's about here. And then if I draw the resultant vector, I started here, I ended here. You'll see that these are about the same length. If I were a perfect drawer, they'd be perfect, and they're parallel. So these two expressions are equal to each other. Now if I want to find s to r, that means I have to start here. So whatever vector I started with has to start here, and then I have to end here, so whatever vector I end with has to, the tip has to end there. So if you look here, this is negative s plus r, or r minus s, and that gives me s to r. Okay, and the last one I need to find is s to t. I don't want to put a sticker on. Let's get rid of this stuff. Okay, so I have to start here, s to t. That's my direction. That means my original vector had to start here. So that again is negative s, and then plus t, which is also t minus s if you prefer that, and that equals s to t. Okay, we're going to talk about one more thing, and that's scalar multiplication. So scalars are numbers like, I don't know, 2, 1/2, 100, 77, -5, etc. You get the idea. By definition, if I have 2 times vector a, that's going to be the same as a plus a. So if I have vector, and actually let's go with this first, and 3a is going to be a, etc. And if I have the scalar -3 times vector a, well, that's like 3 times negative a. So that's negative a plus negative a. That gives me -3a. So if a is this vector here, then a plus a is going to be, or 2a, is going to be a vector going in the same direction as that vector, but twice as long. And just like that. That's a better drawing. And by the same token, if I have vector 3a, well, that's 3 lengths of a. And if I have -3a, well, that's 3 negative a's. So I get the same vector as this guy here, but it's going in the opposite direction. This one's going in this direction, this one's going in this direction. Other than that, they're equal, and if I added them together, that would make the 0 vector. So to wrap that up, 2 times the vector A is in the direction of A, but it's twice as long as A. You can see that. That's twice as long as A. 3A is in the direction of A, but it's 3 times as long as A. And then negative 3A is 3 times as long as A, but it goes in the opposite direction. All right, so given the following vectors geometrically, we're going to find 2r plus s. So r is this vector up here. It moves 1, 2, 3 to the right and up 2. So if I make that twice as long, then my vector r is going to go over 6. So there's 3 more, and then instead of going up 2, it's going to go up 4. So same direction, twice as long. So that's 2r. And then I'm going to add s here. S just goes down 2 and over 2. Oop, overshot that a little. Okay, so my resultant vector starts here, ends here. And that's 2r plus s. Next example, r minus 3s. Okay. Let's see, r goes over 3 up 2. So let's go over 3 up 2. So we'll make r here. I'm going to try to make enough room for negative s. I don't know if it's going to work, but negative s would start here. It would go left 2 up 2. So left 2 up 2, that's 1. Left 2 up 2, that's 2. Left 2 up 2, that's 3. So this is negative 3s. That's not very pointy, but that's supposed to be pointy. And here's my resultant vector. That would be r minus 3s. And this would be negative 3s. So that's what that looks like. Here, I want you to try these. When you're ready, stop the video, try out the problems, and then restart them again. Okay, are you done? Here we go. There's the answers. How do yours look? Well, that's all the fun we have for tonight. We'll see you in 2 days again.